So this is fuzzing, a tale of two cultures. There's two emojis in here. I don't know exactly how to pronounce them, so I'm just going to put in the word two in here. So this being the fuzzing workshop, I thought it would be pretty appropriate to start with what is fuzzing anyway? Well, we think about sending random characters to a program at the system level. That's important. And of course, this fuzzing, as everybody knows, was invented by Bart Miller in 1989 with a very, very seminal paper on an empirical study on the reliability of Unix utilities, together with his students when he tried to figure out how these tools would react to random inputs. Hint, they did not react very well. But the interesting question here is, so the word fuzzing was coined by Bart Miller, but the technique of fuzzing, what is actually new in there? And that's something where I did some homework and actually checked out the bit of the history of test generation in here. So the very first papers on test generation, that is generating inputs for programs in order to test them, already came back from 1950s. So already in the 1950s, there were test routines that would automatically generate inputs. There's the famous paper from 1966, or maybe not so famous paper. This is the first paper that used grammars for producing systematic inputs at the system level. In 1975, we had the first program to generate tests using symbolic execution. That is going through the individual paths and trying to find out inputs that actually solve them. And already in 1984, that is 5 years before the fuzzing paper came out, we already had evaluations of random testing. That is the idea of randomly, of testing programs with random values and random inputs also was there already at the time, which raises the interesting question. So here we have test generation on one side and fuzzing on the other side. What was actually the new thing about fuzzing? The basic techniques, random things, inputs at the system level, all already were present at the time. I tend to think about this not so much from a technical perspective, though, but rather from a cultural perspective. See, when we talk about test generation, we typically talk about people who test their own programs. And this is also true for all the earlier papers that I've shown. So you are building a program and you are testing your own programs, whether it works or not, and you can do so using all various kinds of things. When you're fuzzing, however, typically you're taking an adverse position and you're testing the programs of others. And that is maybe the one thing that was new, because before Bart Miller and fuzzing came along, people would test their own programs, whereas Bart Miller took an adverse position and came and tested other people's programs with one of the simplest methods available, namely simply producing random inputs. And this differentiation is still present today, because in the field of software engineering, we are still mostly assuming that people are testing their own programs, and this is what testing tools are for, whereas security by construction takes the adverse position, where we want to figure out how to find bugs and vulnerabilities in other programs. Software engineers call their techniques test generation, whereas security folks call their techniques fuzzing. But you know, from a technical perspective, there is actually no difference between the two. From a technical perspective, we may just as well equate test generation with fuzzing. And because the techniques used in test generation are the same as they being used in fuzzing. We have search-based techniques, we have symbolic techniques, we have random techniques, model-based techniques, all of these, and we can just append the word fuzzing to them or the word test generation. The difference, though, is in the context. The difference is in the people who use these tools, and there the differences actually are larger. So when you're testing your own programs, being a software engineer in here, well, you want to find bugs. That's clear. That's always the purpose of testing. In your own programs, though, you have an incentive to make your program correct or as correct as possible. So you definitely want to invest lots of time for that, because if your program is buggy, it's not going to sell. You have plenty of knowledge about your program. You have the source code, you have the architecture, you know what it actually does, you know what it's supposed to do. You have a specification in whatever form. You may even have test cases to leverage. You also have an idea where the bugs are, so you can differentiate your program into multiple components, and there's components which are more critical than others, and you know about this. And maybe also important, you actually know what a bug is, because you have an idea what the correct functionality of your program should be. We can certainly agree that a crash or a hang is certainly not accepted behavior, but beyond that, we also have all the functional bugs. And yes, if you're building your own program, you have an idea of what this bug is. And the main thing that you want is guidance. You want what you also want from research, what you want from tools. You want guidance for deciding where to test and how to test. All this is important from your perspective in order to test your own program efficiently. Now look at this from a more adverse position, and I apologize in advance for a caricature I'm putting up here. If you are a security person, say a pen tester, for instance, you also want to find bugs, but for a different purpose. Any time that you invest is going to be expensive. It's also, of course, it's also expensive when you're building your own program. So, but the thing is, you want to find bugs for money, and if your approach does not find bugs, then it's not worth it. You do not have any knowledge about your program. You do not have the source code or anything. Well, at least you cannot assume that you have it. You also have no inputs or traces. Maybe you have some, but the amount of knowledge that you can build on is typically minimal. You have no idea where the bugs are. You may, of course, there may be more critical parts, say input processing or resource interaction or likewise, but generally, no, you don't know that. You don't know that. And you're not interested in functional bugs. You're only interested in crashes. Well, mostly you're interested in crashes because crashes can turn into possible exploits. And for all this, definitely you want full automation, and not just full automation in running your
recording stopped.
Not only having full automation in running your tool, but also full automation in having your test generation approach being applicable out of the box for any program that you can throw at it. Not just your own program, any program, which again means pretty much no common ground and pretty much assumptions as little as possible. And these assumptions actually make quite a difference in the way that we are looking at fuzzing or test generation tools. And in many cases, they are right away in conflict with each other. This is something which becomes apparent when you are writing papers and having them reviewed, because the reviewing cultures build on these assumptions too. And the reviewing cultures then actually can lead to culture clashes in here. So here we have a panel of software engineering researchers. And when you are reviewing for a software engineering conference, and I can tell a bit about that because I have been a happy reviewer for software engineering, for security, for programming languages, sometimes even for machine learning, which is also fun. When you're dealing with a panel in software engineering research, the focus is typically on the future of tools. So a tool is an embodiment of some technique, and the idea is that this technique in the long run will provide some benefit. In particular, when it's being adopted by big players, whatever, when IBM or when Microsoft finally integrate this into their techniques, or when GitHub builds this in their technique. So in 10 years from now, this technique may actually become important. Okay, whatever your paper does, it should provide guidance for testing decisions. So it's not about the actual bugs that you find or the actual performance. It's more like, how will this shape the future of testing? Therefore, the focus is also on conceptual improvements. It's not so much about the concrete tool or the concrete numbers. It's what is it that you bring out that you bring to the table in terms of new concepts, and of course, how is this going to improve over time? If you have numbers in your work, software engineers, having undergone quite some empirical training in the meantime, definitely want explanations on how these numbers come to be. Want details on every single decision and the rationales and how you made this. And in particular, want to know when and why things will not work. This is sometimes surprising. When I'm reviewing security papers, I hardly ever see that. But in software engineering, papers that actually clearly state limitations are super helpful, because again, the idea is that whatever you write, it will eventually be picked up by industry, by professionals, and these professionals, of course, want to know the exact limitations of a technique. If everything is just shiny and polished and wonderful, then this is not, well, in the first place, they're not going to believe you for that. And finally, too, software engineering also has, over time, has adopted quite some important principles of open science. So software engineering reviewers expect you to share your tool, to share your data, and also to make it available during review already. Now I'm going to compare that against the reviewing culture that I have noted, that I have found in security as it comes to fuzzing work. In security, the focus is much, much more in the present than in the future, because security problems are there here and now.
Recording in progress.
And since security, and since the security community focuses on problems that are here in the present, it's obvious that, well, you also need to address things here right in the present. So you cannot easily come up with a technique that will eventually fix things in the long run. No, problems are here, problems are now, problems need to be solved. If your fuzzing paper, or actually pretty much any system security paper, does not come with any vulnerabilities or even exploits, it's going to have a bad time. I once got a paper back and where 3 reviewers told me, this is all such a nice technique, wonderful, everything, but why did you only find existing bugs? Why didn't you show us at least one new bug? Because only then can we accept your paper. Okay, next time we're going to find a new bug. The systems that you work on should be hard. We're talking about binary systems, kernels, device drivers, things where it's really, really difficult to get them set up. You cannot come up and say, okay, I'm having this wonderful Haskell program, and in this Haskell program, I can fuzz it, and my type checker is immediately going to find things. Well, Fox real-world systems with real-world security problems are seldomly written in Haskell, so no. It has to be realistic, has to be big, has to be binary, has to be hard. Assumptions, any assumption you make is going to reduce the value of your work and also the generalizability of your work. People want full automation that can be applied out of the box on anything, from shell to a device driver, to the kernel, or to the Windows kernel, to the Linux kernel, whatsoever. Well, not always, but it should be. Scalability and versatility are king. And we're talking real-world applications, not just some toy program here. Very frequently, it is expected that you show that you are better than others. If you come along with a concept that is all new and where you have no work to compare against because it's so revolutionary, you're going to get into trouble. Well, that's actually also true. Where sometimes we're in the software engineering community, but people actually want comparisons, and you should show that your tool is 10% better than whatever else is around. And also, if you're reviewing, if you're reviewing in security, it's very common to make tools and data available only after acceptance, which is a tradition which comes from the disclosure the disclosure politics of real vulnerabilities. You have a real vulnerability, your vulnerability is worth money, and therefore you're only going to disclose it after your paper is accepted. For fuzzing tools, I rarely see a rationale for that, but these are things that also are slightly different. So these two cultures of reviewing also conflict with each other. Because suppose you are a software engineering researcher and you write a paper, and in your paper you come up with a new fuzzing technique that needs nothing else but a full formal specification of something. Okay? Could be cool. If you submit this paper to a security conference, the reviewers are probably going to stop reading at the word formal specification. Well, what's going to happen to your paper is it's likely going to be rejected outright, because if you're in security, you don't want assumptions. You want full versatility. You don't want to first write a program or a specification or anything. No, your tool has to be fully automated. Likewise, if you are a software engineering researcher and you come along and you say, I have a great Python fuzzer that improves code coverage by 50%. Yeah, well, that would be pretty cool, actually, in the software engineering world. In the security world, with a paper like this, you're going to have trouble again, because, well, Python, who uses Python anyway? Are there any networking systems, operating systems whatsoever using Python? No, not going to work well. Plus, your tool improves coverage. Coverage is an artificial thing. What counts is a real bug. If you didn't find a new bug, or better yet, a vulnerability in the Python interpreter, or likewise, you're going to get into trouble. So this also is not going to work well if you are not willing to adhere to the concepts of the respective culture. You can also go the other way around, by the way. That's also something I experience again and again. You're a security researcher, and you're sick of the reviewing culture of security, so you try sending things over to software engineering, where grass is greener, and you're super proud and you applied fuzzing on some system and you found 3 new CVEs. Come on, how cool is that? Who can do that? Okay, you send this to software engineering. Proud as you are, there goes your paper. And what's going to happen again? Oh, your paper will be rejected. Why will your paper be rejected? Because, well, it's nice that you applied fuzzing on some system and you found vulnerabilities, but that's what testing does, right? I mean, anybody knows if I test something, I'm going to find bugs. So where's the novelty in your approach? And simply applying something on some system, well, that's interesting. That's a nice proof of concept. But first and foremost, the software engineering folks expect you to focus on what's new in your approach. The fact that you found bugs is merely a proof of concept. That's nice. It shows that it scales. It shows that it works. But what is there? What is the concept in there that works? Also, how did your CVEs come to be? Can you come up with an explanation? Or did you possibly know these CVEs in the first place and possibly adjusted your approach such that you can actually find them? And it's nice that you found them. Are there any conditions under which you're not going to find them? So if you modify these parameters, or if you search elsewhere, are you still going to find these? People typically, people in security typically come out victorious. I found the CVE. See, I'm good. My tool is good. Everything. And software engineers tell you, well, under which conditions? Go back and try again and see whether there's conditions where you do not find these CVEs. Oh, yeah. Well, lots of extra work. But bad thing. Okay, this person is going to send things to a security conference again. Another thing, also pretty typical, after hyperparameter tuning, our method performs 10% better than the competition on the benchmark. Assuming there is a benchmark, okay? Typically, it's not a benchmark. It's a benchmark I conveniently defined for this particular set, or at least it looks like it, or it may look like it. And then again, software engineers being trained in empirical research, well, they're going to look at your paper, and then they're going to flame you, because they want to know which benchmark, where did your benchmark come from, how did you choose your benchmark, what kind of hyperparameter tuning, how did you tune these hyperparameters? Is there a process by which I can do this in a systematic fashion? How can I make sure that your method does not over-specialize towards the benchmark you're using? I mean, you're training your method on the benchmark, and then you're testing it on the very same benchmark. And where's the surprise in that? I know that in machine learning, such things are all common. That's all fine, but software engineers want a clear separation between training sets and testing sets and empirical setups and everything. Yep, and they're going to blame you for that. Strictly speaking, if your evaluation informs the design of your technique in any way at any point in time, then, well, strictly speaking, it's not an evaluation anymore, because, at this point, well, as soon as there's some information flow in the other way, you're already tuning your approach towards the evaluation. And, well, that's something you can do, but if that's something you do and you do not report this in your paper, then, well, people may get upset about that. Also, difference in cultures here. This is also why software engineers then expect you to provide your tool, provide your data. Possibly they will even toy with it, and they may even read the source code just because they can. Well, I hope they can. So you see that this difference between test generation and fuzzing, or software engineering and security, can actually run deep. And this is mostly motivated by this difference of testing your own programs versus testing other programs. So we, being the fuzzing community, actually should work against such kinds of divides and such kinds of clashes. One thing we can certainly do is come up with better empirical standards, such as pre-registered reports, as we have it here in the fuzzing workshop, for instance, but also simply mingling up with each other and talking to each other, which we also do here at the workshop. And maybe generally take the perspective that fuzzing is not just about testing own programs versus testing other people's programs, but rather test any program. We want techniques that are able to test any program. And once you do that, when you think about fuzzing tools as tools that you can apply anywhere on your own programs, as well as on other people's programs, then the difference between the software engineering perspective and this security perspective actually vanishes. We can all drop our masks and just be humans again, and here we go. For the rest of the talk, I'm going to continue putting up masks, though, because this is slightly more entertaining. So let's talk about testing any program. How can we build tools that test any program? Okay, so what we need first is, in doubt, we want full automation. We want to be able to apply our testing tools, our fuzzing tools, out of the box to anything. This is the security perspective. On the other hand, we also want control. Control, this is the software engineering perspective, means things like, if we have some inputs, if we have traces, we want to use them. Okay, good. If you're using AFL or any kind of evolutionary fuzzing, you're going to need inputs and traces also, because, well, without given inputs, you're going to have a hard time. Mutating these out of thin air in order to get a valid input. But still, anything that's there, you should be able to use it. If you have access to the source code, we should be able to use it. If we have a specification or test cases, we should be able to use them in our fuzzer. If we have an idea of where the bugs are, we should be able to control our fuzzer such that it actually directs its efforts towards these very places in the code. If you have an idea of what a bug is, beyond crashes and hangs, if you have an oracle, if you have any kind of specification that can tell you, here's a bug, here's not a bug, we should be able to use it just as well. And of course, the fuzzer should go and try to find these violations. All these things should be part of our fuzzing tools, or at least we should have fuzzing tools that allow both full automation, but also control over what's being done. This is my message for you for the fuzzing workshop, for future directions. And speaking of future directions, I'm happy to give you a sneak peek into things that we're currently working on and where we actually try to realize this vision of allowing full automation on one side and control on the other side as well. What we're working on is techniques that allow you to specify inputs, specify input formats. This is classic. This is the field of formal languages, and we're happy to use grammars for that. Here's a grammar that describes the structure of XML inputs, for instance. So what you have here is, what is an XML tree? An XML tree is either a tag that includes both open and closing, or you have an opening tag followed by some XML tree and followed by a close tag. And these tags, what is an opening tag, for instance? A tag is, well, this being XML, is an angled bracket within where we have an ID in there, or you have an ID followed by a set of attributes in there. It's not too difficult to specify these things in a grammar. And if you use that, then you can easily generate inputs from that. You turn the grammar into a producer, and the producer will happily produce strings that looks like these, for instance. So here we have the opening angle, we have a tag O, then we have an attribute CFG, whatsoever. Here's another tag QR, here's a closing tag /P, and so on. This is all neat. And of course, when I say the word specify, then this becomes a very attractive thing for people who are doing software engineering research, not so much at all for people who do security research. We had that earlier. But I can tell you, software engineering folks, we specify something. Oh, we have a specification language. Oh, we have a modeling language. Oh, I love that. If I am a software engineer, that is. Okay, but to make things clear, the fact that you actually can exercise control is also interesting for security researchers, because with a grammar like this, you can actually also direct your fuzzer to produce plenty of interesting payloads in there. Because, for instance, if you say that the text that I'm putting in here actually can consist of the string drop table students followed by dash dash, this means that as soon as you have a rule like that in your grammar, you can easily create one SQL injection string after another, thousands of them. And you can actually also write a grammar for all of your payloads that you want to throw in there. And yes, these are things which are also, again, very interesting if you look at things from a security perspective. That's not something we are frequently talking about when we talk about fuzzing, because this kind of generating inputs that are malicious, that may, for instance, here alter your database or whatsoever, this is not necessarily in the realm, because you need a specification in the first place. Yet this can be super powerful. On the other hand, such grammars as they are limited. And they are already limited when we think about our XML example, because what we have here is actually not XML. This is not XML. And why is this not XML? Well, very simple, because the IDs of the closing tag here, the P, and the opening tag, the QR, they do not match. And in XML, this is required. The closing tag must match the opening tag that we have seen before. And interestingly enough, the fact that an opening tag matches a closing tag cannot be expressed in a context-free grammar alone. You could, if you had a palindrome, so if the closing tag would actually be the reverse of the opening tag, then you can think of it. No, you cannot. You can do so if you have a limited vocabulary of tags. So if you do HTML, for instance, then you can actually enumerate those tags, and then you can, okay, you have plenty of, and then you have plenty of parentheses. But for general XML, this doesn't work. Neither can you specify things like arithmetics, or you want specific attributes to be whatever prime numbers or like things. They're not going to work with a context-free grammar. So, and since we always felt a bit limited with that, we have come up with something new. Our idea is that we take such a grammar that specifies the syntax, and now we go and we add constraints to it, constraints over individual elements in an input string. And these constraints then specify semantic properties. And with these constraints, then we can actually go and produce valid XML, for instance, by adding a constraint that tells us that the opening tag should always be identical to the closing tag. And then the outputs we get here is clear, QR over here, QR over there, opening tag always matches the closing tag. This now, what we get in here is actually valid XML. Let's take a look. Let's take a look a bit more into this constraint, what this looks like. This is all very much still in the works. This is still lab work. It works though. What we have here is a clause that tells you for all trees in our input, for all XML trees named tree, which have the form of an opening tag with a couple of XML attributes, followed by an inner XML tree, and followed by a closing tag. You see, both of these are IDs. We name these IDs. This is the opening ID, OPID. This is the closing ID, CLID. And with that, we now can identify these elements in the input. And here we have an SMT syntax formula that tells that the opening ID and the closing ID, both being strings, must be identical. And this constraint now is being applied all over the place while we are generating inputs. For this, we have built a fuzzer and a language and a checker, which all are named ISLA for input specification language. And ISLA, actually at this point, ISLA is more of a library than a standalone fuzzer because it can be so versatile. ISLA takes a grammar, as we have seen, and constraints. And then, well, it's a fuzzer. It produces inputs. It produces inputs that satisfy both the grammar and the constraint. And these constraints are actually constraints that go into a constraint solver, specifically the Z3 constraint solver at this point. And yes, you can put in quite a number of constraints in there, and the solver will happily take care of them. And not only can ISLA produce inputs that satisfy these constraints, it can also check existing inputs whether they fulfill these constraints. So you can also use it as a checker, which is actually way faster than using it as a producer. This goes practically in parsing time, so no extra time for that. This allows you to use a specification of inputs that is fully declarative. So you have one specification which you can use for both producing and checking. This can be paired with any fuzzing strategy, so you can use all sorts of feedback. You can use all sorts of feedback strategies, or evolution strategies, search-based, whatever strategies as you like. And to give an idea of how complex these specifications are, so we built a couple. For XML, we need 18 lines of code, 18. For tar, so this is GNU tar, we need 61 lines of code. And these 61 lines of code get you a complete fuzzer, a complete checker and parser, and a complete, and of course, a complete foundation for building the smartest fuzzer on top of all of that. So you don't have to write your tar fuzzer from scratch. No, you can just go and say, okay, this is what the input language looks like. Dear Isla, take care of this. And since this also gets you a parser, you can also go and parse existing inputs and then mutate them and then crank them out again, all using, you can mutate things, all while staying syntactically and semantically valid, which is lots of fun. So as I said before, this is still like the dream tool for people in software engineering because, it uses specifications. How cool is that? Mind you, people in software engineering also like full automation. So do we really have to specify all that? Turns out we also have a tool for you. We have also built a second tool on top of that. This is called islearn, which is a pun on Isla. And islearn is a tool that actually produces such constraints. What islearn does is it takes a grammar, again, the grammar. By the way, in earlier work, we have also built tools that can mine such grammars from scratch, from existing programs. So grammars is also not something that you need to specify. If Rahul Gopinath is here in the room, please talk to him about Mimid, and he will happily tell you the great work that he and I did on that, mostly he. And now let's get back to islearn. Islearn takes the grammar, and then it uses this grammar to parse a set of given inputs, and then it checks whether specific patterns, invariant patterns, constraint patterns, actually are being satisfied in these inputs. For instance, it checks whether there are two words or two elements in the input that are always the same. And this is how it can learn the constraint that applies to XML inputs, because the opening tag and the closing tag are always the same. It also checks whether possibly some field is the length of other fields, or is the number of elements in some other element. So all these constraints that typically also apply to binary inputs, def use constraint, checksums, okay? All these things are things that islearn can find by matching these patterns. And then it produces the constraints that you can then feed into Isla and happily again produce more valid inputs. And the nice thing is that these constraints that islearn produces are actually all validated, because it uses Isla with these candidate constraints and tells, oh, I have an idea here what this constraint could be. Could you please validate that? And then Isla validates that by producing inputs that adhere to these candidate constraints, feeds them into the program of choice. And if there is a constraint candidate which does not always hold, then it gets eliminated, which is pretty fun. Okay, we had that length constraint, checksum, diffuse, and more, and we learned languages for Racket, for dot, ICMP, Internet, with an accuracy something between 80 to 97%, which is awesome for producing valid inputs. So from a security perspective, from a full automation perspective, well, in practice, what you need is inputs. Grammar can be mined, patterns are given, inputs. So you are in the same situation as with AFL or like tools, except that, we are doing this not just at a lexical or binary level, we're doing this at a syntactical and semantical level. And once you have these constraints, every single input that you generate is going to be valid. So there's no need to do the shotgun approach of producing millions of inputs in order to find out which ones actually increase coverage. No, each and every single input is going to cover some other part. And since all of this is so nice, I'm happy to give you a short demo of things. So let me switch over to my well-prepared demo over here. So here we go. So this is a Jupyter Notebook with Isla in it, and I'm just checking things, whether things work. So in order to get things done, There's a package which you can import. So you just write import Isla in your Python program, and then you can immediately go forward. Isla uses grammars from the fuzzing book package. Thanks of Rahul Gopinath, Christian Holler, Gordon Fraser, and myself. Look this up if you're interested in grammar-based fuzzing. Here we have a grammar for XML. This is precisely the grammar as we have seen before, with one extra, namely we also have a special word here for users, but we'll get to that in a moment. Okay, is it valid? Yes, it is still valid. That's great. It was valid yesterday. It's valid today too. Okay, and now standard stuff. We use a grammar-based fuzzer, and we use it to fuzz things. And let me just start things again. Sorry, I need to run this from the very moment. How do I do that? I need to stop the kernel for a second. Where do I do that? Oh yeah, shut down kernel. Here we go. Wonderful. Okay, and now I want to run things up to here. Does this actually work? See, never change a running system. Restart kernel and clear all outputs. Here we go. See, that's the fun thing of running a live demo. Okay, here we go one more time. Okay, here we have it. So this is a first input that is being generated by our fuzzer. This is standard grammar fuzzing without any constraints or so. And here you can see here's the opening tag, F54 something. And you also has a closing tag, \h, and you see that the opening tag and the closing tag do not match. Standard stuff. This is not XML. Now we go from fuzzing book, grammar fuzzing, to Isla. Here we have our beautiful constraint. Actually, I'm going to share this stuff after we're done with this talk. So here's again our constraint. And now we can go and create this constraint. Here's the balance constraint. And this parses this very string here. And this is exactly the constraint as we have seen it on the slide before. Now I can start the Isla solver. And the solver now is going to happily produce inputs for me that actually satisfy all these constraints. So you can see like this one, for instance, we have B and H and not B. So this is opening, closing all day long. And yes, it happily creates closing and opening tags that match, which is lots of fun. So, and now with this, your XML inputs are no longer going to be rejected as being invalid, but you actually get deep into things in here. And here's another example. You can also go a bit further. You can also say, okay, I want specific inputs where specific fields satisfy specific constraints. What we have here, for instance, is inputs where the user ID field is twice the group ID field and the user ID field is greater than 1000. So here's one. So the first thing here is, this is again SMT syntax, Lisp syntax. So if I convert the user ID to an integer, if I convert the group ID to an integer, then the user ID should be twice the group ID. And here we do have the user ID should be greater than 1000. Here we go. Again, I can create a solver and I can easily create inputs that satisfy this particular constraint. Need to wait a moment until it gets into users. Okay, here we have one. User UID is 4102. Group ID is 2051. Okay, let me check. 2051 by 2 is 4102. Thank you so much. Is it also greater than 1000? Yes, it's also greater than 1000. See? And now we get more user IDs and more user IDs, and they all satisfy these constraints, which is also fun. And if you have been looking at this very carefully, you will notice that this now is no longer HTML because, this is no longer XML because, we now only have the constraint for user IDs, but we do not have the constraint that the whole thing should be balanced anymore. So but what we can do here is we can combine these two. I want user constraints and I want balance constraints and maybe even more constraints as I have them. And then I can combine them. And then the solver is going to happily produce even more of these. By the way, if you just notice that you have to wait 1 or 2 seconds before the solver starts producing things, that's because in real life, you would actually tune things towards a specific thing. This tuning takes 3 minutes and then it's way faster, but I don't have 3 minutes right now. So we're having fun in producing inputs like crazy. And so you start with the grammar, you put up the extra constraints, and you can have inputs as you like, system inputs as you desire. So let me get back to the end of the demo here. Here we go, back to our slides. Okay, all this is what I call taming fuzzers, namely getting control over what a fuzzer is doing. So tools like these that we're building here allow you to learn constraints from inputs, which is useful because the more inputs you have, the more constraints you're going to learn. We can also learn grammars from program code and inputs, or even without inputs. These specifications are for you to read and edit and manipulate in order to test specific things, which is important for pen testers just as well as for regular testers. If you know that there are specific inputs or specific features in your program that are prone to bugs, you can manipulate these specifications to direct generation towards them. And last but not least, this is an idea which we are just starting to work on. You can apply all these checkers also to outputs. This allows you to specify what the correct behavior, the correct output of a system could be. And then you can have a checker that checks the output just as well. You specify the whole thing. And well, then your fuzzer all of a sudden becomes a full-fledged testing tool. So plenty of things that are in the pipeline here. And this, of course, the combination of full automation and full control is something that we assume may cater to security researchers and software engineers alike. Okay. I want to put praise where praise is due. This whole work on ISLA was implemented by one single person, which is my postdoc, Dr. Dominik Steinhöfel. He has built the entire tool. He has done all the work of putting up the constraint solvers and all. He has filed 500,000 bugs with the Z3 constraint solver. He has built his own constraint solver on top of Z3 and everything. We have a paper that describes all of that. It's called Input Invariance, and we do have a link in here, and such that you don't have to frantically find out where the link is. There actually is a QR code, and you can now take a nice little photo of the QR code, which allows you to find this in your own, in your own library right away. So if you now in the room, if you throw up your mobile phone and follow that QR code, you will have the paper right away in your browser. So, and by the way, the paper also contains links to the implementation of ISLA, to the implementation of islearn, including the examples which I have just shown you. The QR code will show up again during the discussion, no worries about that. So, this was it, folks. Fuzzing, a tale of two cultures. What I've shown you is the culture of testing your own programs versus the culture of testing other programs. What I've shown you also is practical advice. What happens if you send papers to a research community that focuses on one or the other side? I have shown you how to come up with future techniques that actually satisfy or that try to cater to both testing your own programs as well as testing other people's programs, and including the link to our recent paper on the subject. And finally, the concept of linking together full automation and full control all in one package. I also should point out that we at CISPA are also of course trying to make systems as reliable as can be, whether they are written by yourself or whether they're written by someone else. And we are hiring at all levels. I'm hiring PhD students, I'm hiring postdocs, we are hiring tenure track faculty, we are hiring tenured faculty. And if you're interested in working on any of these subjects, say with me, for instance, please let me know. You also have Marcel Böhmer, he's my past postdoc in the room. You have Rahul Gopinath, who's also my past postdoc in the room, and talk to them what it's like to be at CISPA, what it's like to work with me. And hopefully, if things work well, and if you are convinced, please contact me, and I'll be happy to talk to you. That's all, folks. Thank you very much. It's been a pleasure, and I'm happy to take any questions.
Thanks, Andreas, for the wonderful talk. So we have some question. First, Matthias Payer asked, IMO Andreas is missing one of the key points about distinguishing fuzzing from test generation. Fuzzing focuses on bugs that are reachable from attacker-controlled inputs, that is vulnerability. This allows partial concretization of the environment and guidance. I would like to discuss the difference between bug hunting and vulnerability hunting.
I actually think that test generation is something that makes by far most sense at the system level, because the thing is that if you generate tests at the unit level, you always run into the risk of violating some built-in or some assumed precondition. So what I'm talking about here is generally system testing, and this is where it doesn't make much of a difference whether you're hunting for vulnerabilities or whether you're hunting for general bugs. From my perspective, vulnerabilities are bugs, but they're very interesting bugs and very expensive bugs too. So, and many bugs that you find that are not vulnerabilities are not going to get as much attention as vulnerabilities do. So it perfectly makes sense to focus on vulnerabilities and also devise special techniques that say, look for particular critical parts in there. But from a more abstract view, what we're all doing is we're trying to find bugs in systems. And we also need to go beyond crashes and hangs, because say information leaks, for instance, think Heartbleed or privilege escalations as say Log4Shell. These do not manifest themselves in crashes or hangs. And actually, that's precisely the problem, that they do not manifest themselves this way, which is how they can go unnoticed. And we need to come up with techniques that are able to find those.
Matthias, do you want to pitch in? He has actually one more question. At what stage are the filters applied? Will the grammar generator will produce the initial invalid inputs? It may be faster to run the target program with the invalid input if the execution is extremely cheap.
Yeah, that all depends on how deep you want to get into your program. See, if you run a grammar fuzzer by itself, for instance, a grammar fuzzer by itself can generate millions of inputs per minute. So that's, if it's well done, so that's simple. And if, like you, Matthias, convert grammars into a regular expression, then you have a finite state automaton, and then you can probably be again 5 times faster or so. But the thing is, how fast is your execution? How fast is your test program going to be? There will be situations in which an execution only takes a microsecond, and there you go. And then it may be easier or more effective to take a shotgun approach. But it may also be that one single execution takes a minute, maybe an hour, or maybe even the system that you're testing has a built-in limit for the number of tests that you can run on. And this is where approaches that are more sharpshooting are way, way more effective.
Cool. I'd like to jump in now that I have a microphone in hand. So this is amazing. Thanks for the explanation before. With the grammar generation, I think for the first question, I think we kind of disagree. For me, there's a difference in communities is much more rooted in the in the distinction between what you are looking for, right? For a security person, I don't care if you have, if you find a bug in parsing a configuration because that's not a security relevant input. But it may be very much interesting from a software engineering perspective because it's still a bug that should be fixed, right? So for me, that's one of the distinctions that we can look at. But this is very, very philosophical, and this is we can discuss this over a beer or something. The second part was the input generation. What I would like to know much more is, can we define properties on the grammar so that we can create these inputs much faster and much better, potentially extracting subparts from the program for the parser stage so that we can kind of tie these things better together? Because simply throwing a SAT solver at grammar pre-validation may be a little bit more expensive than what we would want to have. And there may be something cheaper along the way so that we can create higher quality inputs, and I think that's what you're aiming for. And I wondered if you thought about this, or if you yes, program slicing or whatnot, and other approaches, and it could be a good way to discuss.
So I can tell you that. So first, I object against the word simply bolting a constraint solver on a grammar. Because
there's obviously a lot of work that went into this, and it's amazing work. I like what you're doing.
Simple at all. There's lots and lots of things that you need to do at this point, but the thing is that there are plenty of cases where you can bypass the expensive constraint solver and immediately come up with a solution right away. So, as I said before, if you have a well-optimized grammar fuzzer, you can produce millions of inputs per minute. Okay, and well, make it another 5 years, and it will be millions of inputs per second. The thing is, there's constraints which are very simple to satisfy. And a constraint such as equality of two things is one of these things, because this simply means that if your grammar fuzzer has instantiated the first of these two tags, well, then it knows then it can instantiate the second one too. And what Rahul Gopinath, I hope he's in the room, and I have been working on, for instance, is converting those fuzzers into programs which then generate these inputs very, very quickly. And the idea is that you have a couple of constraints that you can immediately turn into programs as well, and then also generate these 100,000 of inputs per second, whatsoever. And only if you have a complex constraint that is not easily solvable, make that, this is a prime number, this is the product of two big prime numbers which are larger than whatever. This is very easy to specify in SMT solver, but of course it's rather difficult to find an input for that. But this is something, at some point, you simply want to offload these things to an SMT solver, because the SMT solver will happily dig through things such that you don't have all the load for that. So there will be simple constraints, in particular, close to syntax, which will be easy to solve. And there will be more complex constraints, which will be harder to solve. And these harder to solve things will still take time.
Cool. Thank you very much. I'm a big fan.
All right. Nathan Doughtenhan from Rice University. Really excellent work. I've really appreciated your insights through your different posts here and there on Twitter and so forth about the security versus software engineering communities. So I'm trying to learn a lot, banging my head against the thing. But my question here, I'm new to fuzzing. And I'm here to represent the person who has no clue what's going on. Maybe some students would join me. But so you present ISLA, and you mentioned the problem with the context-free grammar. And I'm kind of intuiting that the issue here is that you're saving on time. But I actually don't really understand exactly why you need to have a second constraints level to kind of, I guess it's search space, but I have no idea. So could you describe to me a little bit how this works and how they kind of form this big picture?
Yes, so this is a question of, so if you want to produce valid inputs, okay, what can you do? Keep in mind that most fuzzers actually not only produce valid inputs, but actually also want to mutate existing inputs, okay? Because if you mutate existing inputs, this actually is one of the efficient strategies. So you want something that is both able to parse existing inputs, but also produce valid new inputs, okay? And this is what makes all the trouble, because, well, anything that goes beyond the next level over context-free grammars would be some universal grammar, or generally a Turing machine, that is, you're programming things. And of course, you can program a program that produces valid XML. That's mildly complicated, okay? But that's feasible. But now you want also a program that can parse XML, mutate it, and write it out again. You can do that too, but then you're in for, I don't know, maybe a day of work if you use existing parsers and producers. If it's a new language, you're in for a week of work, and until it's correct, it's going to take you 2 weeks. And then you have something that works only for one specific domain. Okay, you can do the same for configuration files. You can do the same for INI files, for CSV files, sure. But that's always a couple of weeks of work. And even if you do so, you don't have any strategy on top. You cannot combine this with whatever search-based strategies, coverage-based guidance, whatsoever. Okay, this is why you want these things to be separate. You want one single representation from which you can derive a parser, from which you can derive a producer, both of which then could be combined with arbitrary strategies. And it turns out there's not that many alternatives out there. So the field of programming languages has produced a couple of alternatives, attribute grammars notably. There's also some very small concepts such as grammars that actually come with built-in constraints that can produce things up to a particular level. You're going to find these in the paper, and there are not many alternatives to that. What we are doing here is we think that programmers are familiar with the concept of grammars. Any RFC contains grammars, so that's where we go for. And we also assume that they are familiar with the concept of expressing conditions. Whether this has to be a Lisp-like condition or likewise, this is not necessarily it. We can come up with some syntactic sugar on top of that to make this even easier to use. But we think that this combination is actually the way to go in order to specify, not to separate the syntax and the semantics as it comes to program inputs.
Excellent. So then just to summarize in one sentence, the here and now benefit is weeks of work, and the software engineering benefit is you're systematizing this step of the process.
From a here and now perspective, yes, you can take the code which you just presented and start toying with things. However, until all of this becomes a super polished, super efficient tool which you can apply without first running your whatever Python sentences and whatnot, this is still going to take some time. But we are always happy to have contributors who build on top of that.
Awesome. Thank you so much.
Pleasure.
Hi, Andreas. Roland Yap from National University of Singapore. Okay, nice talk. Just some observations, actually. So for old-timers, I guess we can be considered old-timers, is that, it's a bit like, you used to believe in, specifications are all you need, and then, you turn that into code, perhaps automatically. And the ISLA is nice work, which sort of goes back to, making that circle again. And that was my observation. Back to Matthias' question, and I think maybe from putting the security hat on, there was also one more observation for the two cultures. You could add a third culture, which if you put in proper PLDI, then you might have another clash again. Okay, but so back to the security hat, I think, if you are looking at binaries and so forth, then, things are a little bit different and maybe much harder than what people think. And perhaps fuzzing shows the power of just black box with low-hanging fruit. But I agree that much more work needs to be done, and perhaps some of the things you suggested could be applied, but more from a binary perspective, perhaps, which is quite different from the ISLA one, which is perhaps more from the programming perspective.
I can add a bit to that. You see, most bugs that fuzzers find these days are in input processing, notably in the processing of invalid inputs. So buffer overflows, missing checks, whatsoever, okay? That's all fine. But if you want to go beyond input processing and systematically cover code that is being used after the input processing. This is when things get really difficult, because that's when you need not only some valid inputs occasionally, but you need plenty of valid inputs that also cover an entire set of features here. And this is the kind of inputs that we are focusing on.
Correct.
Because creating invalid inputs is not difficult. It takes 5 lines of Python and you have a Miller-style fuzzer. There you go. It's creating the valid inputs that still get you functional bugs and functional vulnerabilities that are the difficult ones.
Right. So, I mean, certainly valid inputs is important, because otherwise you cannot get into a certain code path. But perhaps from the security hat, one also needs to consider exploitation. And that is, if you look at Log4j, right, that's exploitation. It is valid input. In fact, it's not a bug, it's working as designed. There is no bug, right? I mean, they introduced the feature.
Well, starting an unrestricted shell from... you don't have to wear a security hat to find that difficult.
If you roll back the patches and see, right, someone asked for it and they gave it to them.
Yeah.
Okay, thanks.
Okay, so we are running late, so we have to probably stop. Can we do something like really quick within a minute?
Yes, I hope so. I'll try to be short. Now, a very interesting question that we have, this is also a philosophy question, but towards the grammar generation part. Like what Andreas now greatly presented, and what I actually like is that you can create high quality inputs, throw it at the program, and then run through it to get past the parser stages, to get past the processing stages, to get past the filtering stages and whatnot. Why can't we rip the program apart and only look at the part that we want to look at, and then automatically create, we already have fork servers, right? When we create a fork server, we modify the data layout and then mutate the data layout that the application already has. Right? So we can sidestep all this process and then pay a little bit more attention towards the processing. Now, the most interesting question to me here is how to reduce false positives. And maybe Andreas has some insight here.
Actually, these two things are linked to each other. So if you go and want to mutate internal structures, I'm going to give you an example. Think of a compiler, for instance, okay? Compiler, classic, input source code goes in, gets parsed, becomes an abstract syntax tree. All sorts of optimizations are applied on that tree. And then eventually this tree gets sent out again in order to be converted into machine code. That's compiler 101 in 20 seconds. This tree, okay, this internal data structure, you do not know what a valid abstract syntax tree is. This is not in the type. This is not in any assertion. This is nowhere. And the thing is, if you have this internal data structure and you manipulate it, and then you manipulate it and you find a bug, that's cool. But the question is there any way for an end user, for an attacker, to get this data structure into that shape? And this is precisely where you get false positives. This is what happens when you manipulate things directly inside your program. You can create bugs. Sure, I put a null pointer in here and the function crashes. Boom. Is that really a bug? You don't know, because you don't know whether the null pointer you have there is artificial and whether it ever can be generated. This is why you could go and rip things apart, but you lack the specifications to find out what is expected and what not. And only at the system level can you throw arbitrary things at a program, because only there the program is expected to identify and reject invalid inputs. Later on, as soon as you're at the function level, that's no longer the case.
Thank you.
All right. Thank you. Thanks, Andreas, for the great, insightful talk. There were probably a couple of questions, but we have to end here. And again, thanks for joining us.